Recording now. Okay, so I'm now recording. Okay, so this is lesson 11. Last class, we concluded with what's called the inversion algorithm. And it says to find the inverse of an invertible matrix A, find a sequence of elementary row operations that reduces A to the identity matrix, and then perform the same sequence of operations on I sub n to obtain A inverse. Okay, and so this class, we're going to start with an example in which we're going to find the inverse of a given matrix using the inversion algorithm. Okay, so example 4 is using row operations and the inversion algorithm to find A inverse. Okay, so solution. So we want to find the inverse of the following matrix. We want to find the inverse of A equals, and so the entries are 1, 2, 3, 2, 5, 3, and 1, 0, 8. So we'll find the inverse of that. So we're going to do this on the whiteboard. But let me just write this here. So what we want to do is we want to reduce A to the identity matrix by row operations. And at the same time, simultaneously, apply these operations to the identity matrix to produce A inverse. Okay, so that's the goal of our procedure. Okay. To do this, start new in here. To do this, we will adjoin the identity matrix to the right side of A. That produces a partitioned matrix of the following form. So what we'll have is a matrix where on the left side is A and on the right side is I. So partitioned means you're separating it into two parts. It's separated into parts. In this case, you're separating it into two parts, the left part and the right part. The left part will be the matrix A, and the right part is I. Okay, so what we will do is we will perform elementary row operations to this matrix until the left side is reduced to I. At the same time, these row operations will convert the right side, which started as I, will convert the right side to the matrix A inverse. So the final matrix, so the final partitioned matrix will have the following form. There'll be a matrix where on the left side of the partition is now I, and on the right side is A inverse. Right? Okay, so the computations will be on the whiteboard. Okay. So, but just going over the goal, the general procedure, you start with the matrix A, and you want to find the inverse of this matrix A. So you start with the partitioned matrix, A on the left, I on the right. you perform elementary row operations on this partition matrix so that the left side becomes I. Meanwhile, while you were doing those elementary row operations to get A to I, at the same time, in the same order, you were doing those elementary row operations on I. And by the inversion algorithm, what the inversion algorithm says, if you perform the same elementary row operations on I, that you will get A inverse. The sequence of elementary row operations that converts A to I, when performing the same sequence of elementary row operations on I, you get A inverse. And so this partition means that you're doing these row operations at the same time on two separate matrices. And so you can see the result of those row operations by the left and right side correspondingly. And so this is a fast way to apply the inversion algorithm to a general matrix A to get its inverse. And this works if A is invertible. If A is not invertible, you could apply this, you could try to do this procedure, and then when you prove it fails, you could show that it's not invertible. But okay, but right now we're not worried about that. Right now we're assuming that A is invertible. And we're saying, okay, A is invertible, and let's just find its inverse using the inversion algorithm. So on the whiteboard, we're going to do those calculations. All right. So we're starting with A on the left side. All right, that's why not. A on the left side and I on the right side. Okay, so I put green for that because that's where we're starting. The rest of it, for now, I'm going to put in black. Okay, so what A on the left and I on the right means is that our matrix, which I had on the whiteboard, I'm just going to write it again here. This is A. It was 1, 2, 3, 2, 5, 3, 1, 0, 8. Okay, so this was A. So that was on the left side. On the right side is the identity matrix. And so since we're dealing with a 3 by 3 A, our identity matrix is a 3 by 3 identity matrix. Okay, so A is going to determine the size of your identity matrix. It's going to the same size. Okay, so that's A partitioned with I. Okay, so we're going to now convert this using elementary operations so that we have the identity on the left side. So the identity matrix is a matrix in reduced row echelon form. So we just want to get this matrix on the left to reduced row echelon form. And to do that, we can use Gauss-Jordan elimination. Okay, so let's go through it. So you want to identify the leftmost non-zero column. There it is. Now you want to make sure the top entry is non-zero, which it is. So you don't have to worry about that. And then we want to make all the entries below it 0 by adding appropriate rows, right? So adding constant multiples of rows to other rows. So if you do -2 times the first row and add to the second, then that gets rid of the 2 underneath it. So -2 times the first row, add to the second. This becomes a 0. This becomes a 1. And this becomes a -3. Right? If I do -2 plus 2, it's 0. -4 plus 5 is 1. -6 plus 3 is -6. So I just -2 times the first row and add it to the second. The goal is to get all the entries below this 1 at the top to be 0. So then I'm going to take -1 times the first row and add to the third row. And so I'll get a 0 here. I'll get a -2 plus 0, which is -2. And I'll get a -3 plus 8, which is a 5. And so now I have that. Correspondingly, I'm going to have to, I should have done this at the same time so it's easier to follow. I took -2 times the first row and added to the second. I'm going to do the same thing here. So -2 times the first row, added to the second, and you get this. And for the third row, I took -1 times the first row and added to the third. So I take -1 times the first row and add to the third, I get that. Okay, so by the early steps of Gauss-Jordan elimination, I've now got all the entries below this 1 at the top of this leftmost non-zero column. I got all these entries below it to be 0. Okay, well now either my matrix is in row echelon form or it isn't, and I have to go back to the beginning. So this matrix is not in row echelon form. That's because the third row is a non-zero row that does not have a leading 1 in it, right? The first non-zero leftmost entry. The leftmost non-zero entry is not a 1, and it's a non-zero row. So this is not in row echelon form. And that means we have to start again at the beginning. But before we start at the beginning, we have to cover up the topmost row. Okay, so we're covering up that row. There's a 2 there. That's a 2. This is a 2. Okay, so we cover up that top row. So the pink means it's covered up. And so we're going to repeat the steps from earlier with this now covered up matrix. Okay, so now what do we get now after we cover up the top row? So after we cover up the top row, we identify the leftmost non-zero column. So to identify the leftmost non-zero column, I'm just going to use blue now. So that's the leftmost non-zero column in the submatrix after you remove that top row. The top entry is non-zero, so we're good. It's also a 1, so we're also good there. So we just need to make it so that that entry, the entries below it are 0. So the top entry that we covered up is not going to change right now. So right now this is just covered up, and it's there, but we just don't care about it. It's not affected by the procedure right now. It'll be affected later. The second row is this. And so what's going to change is the third row, because we need the entry below the 1 in green to become a 0. This was the old, that was the original leftmost column. Our new leftmost column is this one. Actually, I'm going to erase that. Okay, so because we're not looking at that at the moment. There was a 0 here. Okay, so so we're going to take 2 times the top row of the submatrix and add it to the second row of the submatrix. So if you do that, this is still a 0. 2 plus -2 is 0, so that becomes a 0. That's why we did it. -6 plus 5 is -1. -4 plus -1 is -5. 2 plus 0 is 2. 0 plus 1 is 1. So now those are the entries. So what happened is that the leftmost non-zero column, which is in blue, the top entry is a 1 and everything below it is a 0. And so now we've done the steps again for the new submatrix. Now, if this matrix is in row echelon form, we can move on to procedure. If it isn't, we have to go back to the beginning. This matrix is still not in row echelon form because the bottom row, the second row of the submatrix, it does not have a leading 1. The leftmost non-zero entry in this non-zero row is not a 1, it's a -1. So it's not in row echelon form, so we have to go back to the beginning again. Before we go back to the beginning, though, we just, according to the procedure, we have to cover up the topmost non-zero row of the submatrix that we're working with. So I've now covered up the second row also. So now there's only 1 row left. So I have to identify the leftmost non-zero column of what's left. And so that's just a single entry -1. And so I need to make that a 1. I need to make the top entry of the submatrix I'm working in, of the leftmost non-zero column. I need to make the topmost entry a 1. So the top 2 rows are unaffected. So right now, because I covered them up. So these two those 2 rows are now covered up. And so I just want to make this 1 here that I've circled, -1, I want to make the 1. So I'm going to just divide by -1 or multiply by it. Technically, it's divide by -1. You can, in this instance, think of it as multiplying by -1. And so then 0, 0, 1, 5, -2, -1. And so the leftmost non-zero column is this brown circle. It's only 1 entry, but it's still a column. It's just a column with 1 entry in it. So I multiplied the whole row by -1, which was technically, according to the algorithm, dividing by negative. You divide by the element, the non-zero element by itself. Divide the non-zero element by itself. So you would divide -1 by -1, multiply by negative. So you have a 1, 5, -2, -1. Okay, so now our leftmost non-zero column has a 1 at the top and 0 everywhere else. It has a 0 everywhere else because there are no other entries. So vacuously, it's true that there are zeros everywhere else. Okay, so now we've done the procedure again for this row. So now we ask ourselves the question, is this matrix in row echelon form? Well, every non-zero row has a leading 1. Every row is a non-zero row, and every row has a leading 1. So property 1 is satisfied. Property 2 says all the 0 rows are at the bottom. That's also true because there are no 0 rows. So it's true vacuously that all the 0 rows are at the bottom. The third property says that every 2 consecutive rows, non-zero rows, the leading 1 and the lower 1 is further to the right than the leading 1 above it. That's also true because there are 2 pairs of consecutive non-zero rows. Each of the pairs of consecutive non-zero rows, the leading 1 and the lower 1 is further to the right than the leading 1 above it. And so it also satisfies property 3. So this matrix is in row echelon form. So this is in row echelon form. So now that this matrix is in row echelon form, we can now move on to the next step of Gauss-Jordan elimination, which is now working backward and working from the bottom up and getting rid of the, making the entries above each leading 1 zeros. So I'm going to continue now in this column, and this column is for the last step, which is to get it in reduced row echelon form. So this first middle column, this column here I was working with, was to get it in row echelon form, and I succeeded. So I succeeded at that there. And now this next column is going to be to get it in reduced row echelon form. So the bottommost, we start with the bottommost row in the last step of Gauss-Jordan elimination to go from row echelon form to reduced row echelon form. And so when we start with the bottommost row, we just have to add, starting with the bottom row, we have to add suitable multiples of it to the rows above it so that all the entries in the column that it's in above it become 0. So if you look at this orange column we're drawing here, this is the column that contains the leading 1 in the bottommost row, and the entries above it are non-zero. I need to make both of them 0. So to do that, I'm just going to add 3 times the bottom row to the second spot, to the row just above it. So if I take 3 times the bottom row and add to the row just above it, that will get rid of the -3. And so now 3 times 5 is 15. 15 plus -2 is 13. 3 times -2 is -6. -6 plus 1 is -5. And then 3 times -1 is -3. -3 plus 0 is -3. So I just took 3 times the bottommost row and added to 1 just above it. Then to get rid of the 3 above that, on the top of that orange column, I have to take -3 times that row and add to the topmost row. And so if I do that, you still have a 1 and a 2 here because there's zeros in that row that you're adding. You're adding -3 times 0 in both cases, which doesn't change the top row. -3 times 1 is -3. -3 plus 3 is 0. So we got that. And now -3 times 5 is -15 plus 1 is -14. And then you keep multiplying by -3 and adding. So you have a 6 plus 0, which is 6. And then you have a 3 plus 0, which is 3. You have 2 negatives, which become positive in both those cases. Okay, so now we have that. Okay, so the bottom and the we were looking at the bottom row and adding suitable multiples to the rows above it. So that was this column. So we've now succeeded at making all the entries above the leading 1 at the bottom of that column into zeros. We're working up. And so now this last row is now done. It's done. We're good because all the entries above the leading 1 in that column, all the entries above that leading 1 are 0. So we're done with the bottommost row. And so then we move to the next row. So now we're going to move to the row above it. So now we're going to look at the second row, and we're going to look at the leading 1 in the second row. And the goal now is to get all the entries above that leading 1 to be 0. So that the 2 is above it, we need to get that to be a 0. So that's the goal now. And so I continue. This arrow means after the matrix is above it. It has nothing to do with this other arrow that's coming up there. Okay, and so now we're going to continue. So the bottom row is done. We're working upward. So if we're working upward, nothing we're going to do now is going to affect the bottom row. We finished with the bottom row. I did a little orange check here because we were done with that because the orange column has zeros everywhere above the 1 at the bottom. So we're working on the second row now. So if we're working on the second row, also, the second row is not going to change because what we're doing is we're adding suitable multiples of the second row to the rows above it. Okay, so what we're doing is changing things above the row we're working in. So the second row stays the same. We just need to make the 2 in the orange, in the red column, make that 2 at the top 0. So we add -2 times the second row to the first, and you get a 1, 0. -2 plus 2 is 0. 0 plus 0 is 0. And then -2, -26 plus -14 is -40. Okay, and then -2 times -6 is 12. 12 plus 6 is 18. Oh, okay, here. Wait, I have to fix something. Here, if here, I took this and I added it here. It was 3 times -2 plus 1. This should be a -5. Okay, so this entry is a -5. The green is just so that's a -5 there. Okay, so when I do -2 times that row and add it to the one above it, then what I get here is a 16. Okay, so that's a 16. Because then it's -2 times -5 is 10. 10 plus 6 is 16. And then -2, 6 plus 3 is 9. And the -5, I just have to put the -5 there from the green earlier. Okay, so you have 5, -2, -1, 13, -5, -3. Okay, so now we have that matrix. So now, we're now done because our matrix is in row echelon form. Well, we're done with 2 things. We're done with Gauss-Jordan elimination because it's in reduced echelon form. But we also basically did what we wanted. What we really wanted was that the left side was the identity, and that the right side would now be A inverse. Okay, the goal was to get the left side to be I. And so I did Gauss-Jordan elimination because that's the procedure that gets a matrix to reduced echelon form. And so if we can get our matrix to I, the reduced echelon form of a matrix is unique. And so if we're getting the left matrix to be I, if that's the goal, then since I is in reduced echelon form, just use Gauss-Jordan elimination because that's the procedure to get a matrix to its unique reduced echelon form, which in this case is I. Okay, and so the left side is I, and the right side is A inverse now, because that's what the inversion algorithm tells us. It tells us the elementary row operations that converts a matrix to I, applying those same operations to the identity matrix, will get it to A inverse. So the right side goes from I to A inverse. And so we conclude then the conclusion of all this work is that A inverse is the matrix on the left-hand side of that partition final matrix. A inverse is -40, 16, 9, 13, -5, -3, 5, -2, -1. Okay, and so that is A inverse. And so I was alluding to the fact that this procedure tells you when a matrix is not invertible also. And so as a note, if a row of zeros appears on the left side of the partition at some stage, at any stage of the inversion algorithm, then you can conclude that matrix A is not invertible. Okay, so the reason why you can conclude it's not invertible is because once there is a row, once there is a row of zeros on the left-hand side, and that means that it doesn't matter what elementary row operations you perform from then on, you can't get to the identity matrix. Okay, it's impossible. Okay. There's no way to get the identity matrix to a matrix with all 0 rows. See that? See the identity matrix? How I have it here? That's a 3 by 3 one. But if you think intuitively, you can see how you can't get that identity. You should be able to get that identity matrix to any matrix with a row consisting entirely of zeros, right? You can only have non-zero rows with elementary row operations. And so the flip side of that is just because every elementary row operation has an inverse operation, the fact that you can't get I to a matrix with any since you can't get I to be a matrix with a 0 row, you also can't get a matrix with a 0 row to be I. Okay, and so once you apply this procedure and you get a row of zeros, that means you stop and you realize that your matrix is not invertible. Okay, any matrix that is invertible, you can convert it to the identity matrix using only elementary row operations. Okay, and if you can't do that, then it's not invertible. Okay, and so the inversion algorithm will also tell you whether or not a matrix is invertible by whether or not the procedure produces a row with only zeros on the left-hand side of the partition. Okay, so let's see an example of that. So let's see an example of when you're applying the inversion algorithm to a matrix that's not invertible. And so what will happen is that it will show you that it is not invertible. There will be a row of zeros. So example 5 is showing that a matrix is not invertible via the inversion algorithm. So consider the matrix A, which is going to be a 3 by 3 matrix also. Do 1, 6, 4, 2, 4, negative 1, negative 1, 2, 5. So consider that matrix. Okay, so applying the procedure of example 4 yields this matrix. So if you apply the elementary row, you apply Gauss-Jordan elimination to that matrix in an attempt to get it the left side to be the identity matrix, then what will happen is I have this vertical line here. So that's the so the vertical line is the partition between the left matrix and right matrix. It's just a small one. Okay, so what you'll end up with is at the top row, you'll have 1, 6, 4. This one. Oh, all right. Sorry. Okay, so you start out with this. You have 2, 4, negative 1, negative 1, 2, and 5. And the right side, you have the identity matrix. Right, and so you just do an elementary row operation on it, and then we'll see what happens. Okay, so I'm going to go to the whiteboard. Okay, so the rest of the computations will be on the whiteboard. Okay, so now we have the partition matrix where A is on the left and the identity is on the right. Okay, so I'm just going to label this as example 4. So this is example 5. All right, so for example 5, you have this partition matrix. The identity is on the right side. 1, 6, 4. 2, 4, -1. -1, 2, 5. Okay, so let's just get this to reduce echelon form and see what happens. Okay, so first you identify the leftmost non-zero column. And you also see that the top entry is non-zero. So you just need to make the entries below it 0. So we're working with the top row. So the top row is going to stay the same. We had -2 times the first row to the second. And so this will become the following entries. And so you'll have that. And then also at the same time, so this is the first column there. This is the topmost entry, which is a 1. And so I'm going to add the first 1 times the first row to the third row. I'm going to add the first row to the third row. That way, this entry is a 0. So then it's 8, 9, 1, 0, 1. Okay, so we now have that. Oh, okay. Okay, so we have that. So now all the entries below it are 0. So it's not in reduced echelon form. So we start at the beginning. Before we start at the beginning, we just cover up the topmost row. And so now we're going to identify the next leftmost non-zero column in the submatrix. That's this. And so we need the top entry to be a 1. And so in order to get the top entry to be a 1, actually, so this is where you can get a little creative sometimes. Now, this is an easy example of being creative, but you start with Gauss-Jordan elimination. I would say is the best bet if you want to make sure you're right. But sometimes you can just skip ahead because something obvious happens. If you're looking at this row and you look at the row below it, you can see how these two entries are negatives of each other. There's a -8, -9, and below it 8, 9. If I just add this row, if I add the top row of the submatrix to the next row below it, I'm going to get zeros below it. And that's what I want. I can see I can make a 0 row. So when there's an easy way to make a 0 row, I want you to just jump ahead, forget about Gauss-Jordan elimination, depending, if it's the right circumstance. In this case, you want a 0 row. And so if you do that, good. So you add this row to the next row. You get 0, 0, 0, and then -1, 1, 1. So now by adding the top row of the submatrix to the second row of the submatrix, I now have a 0 row on the left side. Okay, so you see how there's a 0 row here. Okay, and so the fact that there's a 0 row means that we can conclude that A is not invertible. And so our conclusion is that since we got a 0 row on the left side, we conclude that the matrix capital A is not invertible. All right, that's it. So we started applying inversion algorithm to find the inverse of our given matrix. And we find that we were able, and we did find get the row zeros at the bottom some way. And so since we could do that legally, using only elementary row operations, that means that our original matrix is not invertible. Right, and so that concludes example 5. Any questions about this? Okay, so right, so that's example 5. So next is another example, example 6. And example 6 is analyzing homogeneous systems. So remember, a homogeneous system is one in which all the equations equal 0, right? You have it equals a constant generally, but for homogeneous systems, it always equals 0. The constant on the side is always 0. So use theorem 1.5.3 to determine whether the given homogeneous systems have non-trivial solutions. Okay, so what was theorem 1.5.3? Let me remind you. So this was theorem 1.5.3. It was the equivalent statements theorem. It was this theorem. So I'm going to copy it and bring it over here. It's the one we proved using the chain of deductions. So I'm going to bring example 6 on the next page. And so as a reminder, that's theorem 1.5.3, equivalent statements. If A is an n by n matrix, then the following statements are equivalent. That is, all are true or all are false. A is invertible. B, AX equals 0 has only the trivial solution. And to help you out, I was saying the trivial solution is the one in which all the unknowns in the vector X are 0. All the entries. C, the reduced row echelon form of A is I sub n. And D, A is expressible as a product of elementary matrices. So whether all 4 of these statements are true or all 4 are false, for any given n by n square matrix A, for any square matrix or n by n matrix A, capital A. So we want to determine whether the given homogeneous systems have non-trivial solutions. So, okay, so this is just reminding you. The line I drew before was oh no, never mind. Okay, in between those lines is just the theorem 1.5.3. So the part A here I'm referring to is example 6. So for part A, for example 6, we have this given system. If x1 plus 2x2 plus 3x3 is equal to 0, we have 2x1 plus 5x2 plus 3x3 is equal to 0. And we have x1 plus 8x3 is equal to 0. Okay, so this is our given linear system. The goal is to determine whether this given homogeneous system has non-trivial solutions. Okay, using notation, we can abbreviate this entire linear system as one matrix equation, AX equals 0, where the matrix A is the coefficient matrix of that linear system. And so the A here is just the entries 1, 2, 3. I'm just adding this in to help to explain it. 2, 5, 3, 1, 0, 8. Okay. So if and x, little x is the equation, is the vector of unknowns. So the x here is x1, x2, and x3. And 0, remember I was telling you 0 is weird. the linear algebra, the 0 there is not referring to a number 0. It's referring to a 3x1 0 matrix. So the 0 there is a 3x1 0 matrix. Any 0 matrix is just one in which all the entries are 0. So I can express all of this, x1 plus 2x2 plus 3x3 equals 0, 2x1 plus 5x2 plus 3x3 equals 0, and x1 plus 8x3 equals 0. I can write the whole thing as ax equals 0, where A is the coefficient matrix, this, x is this matrix, 0 is that one. And what you can see is that if you multiply out these matrices, just to explain, I was explaining it last class, but to explain again, what that equation means or says, that equation says that, right? It says that if you take this matrix, which I'm defining as A, and I take this matrix, which is the vector x, and equals this 0 matrix, right? That's what that says when you substitute all three of those matrices, say, right? So what that means is that now if you multiply the two matrices on the left-hand side, when you multiply the two matrices on the left-hand side, you have a 3x3 matrix and a 3x1. So the result is, a 3x1 matrix. Right, 3x3 times 3x1 is 3x1. So if you multiply the two matrices on the left-hand side, you're going to have it's still going to equal the right-hand side. And the right-hand side is not going to change. The right-hand side is still the 3x1 0 matrix. So the right-hand side is just corresponding with what it already was. The left-hand side is now multiplying those two. Now, if you multiply those two, you get x1 plus 2x2 plus 3x3. And then in the next entry, you get 2x1 plus 5x2 plus 3x3. And then the next one, you get 1x1, or just x1, plus 0x2, or just don't write anything there, and then plus 8x3. And so saying ax equals 0 is saying that this matrix equals this one. When two matrices are equal, it says that the same size, which they are, they're both 3x1, and that their corresponding entries are the same, or the corresponding entries are equal. So this one matrix equation is really saying x1 plus 2x2 plus 3x3 equals 0, which is the first equation, and 2x1 plus 5x2 plus 3x3 equals 0, which is the second equation, and that 1x1 plus 8x3 equals 0, which is the third equation. So this one matrix equation is representing all three equations in the given linear system. In order for this one matrix equation to be true, ax equals 0, equivalently, all three of these equations have to be true. So just because I'm representing three equations by one matrix equation, doesn't mean it's actually any less information. Okay? It's just this one matrix representation is equivalent, or says the same thing as three regular algebra equations that you're used to. Okay? So anyway, I can abbreviate the entire linear system as ax equals 0, where a is this matrix, x is that, and 0 is that. So we want to use this theorem to conclude, to say, determine whether or not it has non-trivial solutions. But this linear system is expressed as a matrix equation ax equals 0. B in the theorem is the statement ax equals 0 has only the trivial solution. So we want to determine whether or not ax equals 0 has only the trivial, whether or not it has non-trivial solutions. If it has non-trivial solutions, that means it's false that ax equals 0 has only the trivial solution. Okay? And so what we really need to do is, if we want to determine the truth, whether or not this B is true or false for this given ax equals 0, we just need to show that any of the other three statements are true or false, because all four statements have the same truth value according to the equivalent statements theorem, theorem 1.5.3. Okay, so our job is no longer to directly show that it does or does not have non-trivial solutions. We can show any of the three other ones are true or false to do that. All right. Well, so in examples 4 and 5, in example 4, we had this matrix. It was 1, 2, 3, 2, 5, 3, 1, 0, 8. So that A in example 4, that 1, 2, 3, 2, 5, 3, 1, 0, 8, that's the coefficient matrix right here. That's the coefficient matrix for the system. It's the A in the AX equals 0 matrix equation. What we found in the example 4, well, we found the inverse of it. We found the inverse of example 4. And so I'll just quickly go to the whiteboard. So in example 4, we found an A inverse for it. The inversion algorithm told us that A has an inverse, and we found what it was. So we know from example 4 that the matrix we're looking at now, the same matrix, is invertible. So from example 4, we know that matrix capital A here is invertible. Well, if we know that A is invertible, we know that this statement is true. And by the equivalence statements theorem, that means that B is also true. It has the same truth value. They're all the same truth value, so B does. Well, that means that AX equals 0 has only the trivial solution. By the equivalence theorem, that's another way to say it. That's another name for theorem 1.5.3. Okay. You could say by the equivalence theorem. So by the equivalence theorem, AX equals 0 has only the trivial solution, because that's what B says, and it's equivalent to A. A is invertible, which means that AX equals 0 has only the trivial solution. That statement is true. So if AX equals 0 is only the trivial solution, then that means the answer to whether the given homogeneous system has non-trivial solutions, the answer is no, it doesn't. It does not have non-trivial solution. So thus, AX equals 0, or thus the given homogeneous system, which is expressed as AX equals 0. AX equals 0 is an expression, another way to illustrate, to describe, another way to say what the system is where AX equals 0. So thus the given homogeneous system does not have non-trivial solutions. If it has only the trivial solution, it does not have non-trivial solutions. It's two negatives. Right, so that's part A. Part A is we determined that this homogeneous system has only the trivial solution. It does not have non-trivial solutions because its coefficient matrix A is invertible, and by the equivalence theorem, that means that AX equals 0, or the system itself has only the trivial solution. So part B of the same problem, we look at another linear system. This one's x1 plus 6x2 plus 4x3 is equal to 0. The next equation is 2x1 plus 4x2 minus x3 is equal to 0. And the third equation is negative x1 plus 2x2 plus 5x3 is equal to 0. Okay, so you have this linear system, and so now you just look at the coefficient matrix of that. So looking at that's this matrix. 1, 6, 4, 2, 4, negative 1, negative 1, 2, 5. Okay, so the coefficient matrix of this system. So here, capital A is equal to this matrix right here from example 5. So here A is equal to this, which is the matrix from example 5. So in the matrix from example 5, we found that it was not invertible. Example 5, this matrix is not invertible. Example 5, our conclusion was since we got a non-zero on the left side, we conclude that matrix A is not invertible. So we found in example 5 that matrix is not invertible. And so if we know that our matrix is not invertible, then saying that it is false. So A is a false statement. It's false to say it's invertible because we know it's not. Since they all have the same truth value, the fact that A is false means that B is also false. So AX equals 0, or the matrix equation expression, or the matrix equation, the matrix equation for this linear system, just the way of expressing it as a matrix equation, AX equals 0 does not only have the trivial solution, because saying it does only have the trivial solution is false. Okay, so from example 5, we know that A is not invertible. Thus, by the equivalence theorem, the theorem I'll just point there. Thus, by the equivalence theorem, AX. Let me write everything out. Thus, by the equivalence theorem, the statement that A is invertible. Wait, let me put this in between thing. Okay, so we know that A is not invertible. Thus, the statement A is invertible is false. Okay, thus, by the equivalence theorem, the statement that says AX equals 0 has only the trivial solution is also false, because the equivalence theorem says they all have the same truth value. Thus, since that statement is false, we know that AX equals 0 has non-trivial solutions. It's false to say it only has a trivial solution, so it has non-trivial solutions. The goal of the problem is to say, determine whether the given homogeneous system whether it has non-trivial solution. It does. We're done. Okay, any questions about that? So you can see how the equivalence theorem is helpful to find things that might be difficult to find directly. You can find things that find it indirectly using the theorem. Okay, so that's the end of 1.5. So the next section is 1.6, which is more on linear systems and invertible matrices. This is theorem 1.6.1. A system of linear equations has 0, 1, or infinitely many solutions. There are no other possibilities. So I talked about this early in the course, and we were looking at three space, and we were drawing pictures of subspaces and looking at the intersection of planes and showing how there are only 0, 1, or infinitely many solutions exactly. This is a general case that's true in any situation. So theorem 1.6.1 says a system of linear equations has 0, 1, or infinitely many solutions. There are no other possibilities. It cannot have 2 solutions. It cannot have half a solution. It can't have 5. It can't have 100. It's only exactly 0, exactly 1, or exactly infinitely many. Okay, so let's prove this theorem. Okay, so assume that AX equals B has more than one solution. Okay, So AX equals B is our matrix representation, matrix equation representation of a linear system. Okay. When you have a general linear system, maybe I wrote this down last class so that I can just copy it. I may not have. No. Okay. So I want to quickly just explain again. Oops, wrong one. Okay. The wrong thing. Okay. There we go. Okay, I got it. It's the first day. Okay, so just want to remind you of this, right? If you have a general linear system of m equations and n unknowns, it could be written in that way, right? So the b here is the column vector consisting of the b's on the right-hand side, right? So the capital A is the matrix for all the coefficients, the little a's. The little x are the unknowns x1 to xn, and the little b is the b's on the right-hand side. So below, we have that matrix A is equal to coefficient matrix, where I'm not writing all the entries. I'm just gonna that would be like A11 dot dot dot. This would be A1n dot 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 dot. Okay, so there's gonna be entries in between everywhere. So I have to put in the corner one, so this makes sense. And then this is AM1, and then this is AMN, right? So this would be that would be the matrix A for a general linear system. The X1 would be a column vector, and it would start with X1, and then it would be dot dot dot, all the ones in between, and then it would end with XN. And the B would be an n by 1 matrix also, which I'm abbreviating here, and the entries would be B1 dot 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 up to and including the last entry, which would be BM. Okay, there is an n here and an m there. Okay, so the n here is because there are n columns in the first matrix, right? But the m at the other one is because there are m rows. There are m rows and n columns, so you end up with this. Okay, so you have an a, x, and b. So that's how you have a general. This matrix equation is a matrix equation representing a general linear system of m equations and n unknowns using these matrices here. Okay. So AX equals B is a matrix representation for a general linear system of m equations and n unknowns. Okay. Okay. So brief review. Okay. And so we have that. Okay. So that's explained that matrix equation AX equals B. If it doesn't make sense. So we're assuming that it has more than one solution, meaning this linear system has more than one solution, and we're just representing it as a matrix equation. So we're assuming it has more than one solution, and we let the matrix X naught equal to X1 minus X2, where X1 and X2 are any two distinct solutions. Okay, we can't assume there are two distinct. We don't know whether or not there are two distinct solutions, but our assumption is that there are. So we're assuming there is more than one solution. Assuming there is more than one solution means there's at least two. And so we have the assumption. We can now we're continuing with that assumption. So we have two distinct solutions, and we choose any two we want. So if there were 1,000,000 solutions, or there were 5 solutions, however many solutions there are, there can't actually be 5, only 5. But however many solutions there are, if there were more than 2, we just choose any 2 of them that are distinct. So we're going to let x naught equal x1 minus x2, choosing any 2 distinct solutions among the at least 2 solutions. Okay, x1 does not equal x2 because they're distinct. And that means that x naught is non-zero, right? X naught, which equals x1 minus x2 already, cannot equal 0, since x1 and x2 are distinct, right? So x naught is non-zero. Moreover, ax naught, which is plugging in the difference of those 2 distinct solutions, is equal to a times x1 minus x2, because x naught is x1 minus x2. And now that's equal to, using matrix properties, ax1 minus ax2. Well, we know that x1 and x2 are solutions to the equation ax equals b. What that means is, as solutions, it means just like in regular algebra equation, x1 is something you can plug in for x where that equation holds. It's true. So ax1 equals b and ax2 equals b. So ax1 is b and ax2 is b. So that means ax1 minus ax2 is b minus b, which is 0. So we just showed us that ax naught is equal to 0. Okay, so if we now let k be any scalar, meaning any like real number, so we're going to let k be any scalar, then watch what happens. We're going to take a times x1 plus kx naught. And we're going to see what happens. We're going to take a and multiply on the right by x1 plus kx naught. Well, that equals ax1 plus a times kx naught. Just have to fix the parentheses. Kx naught. There we go. Okay. And this is equal to ax1 still, plus, and I can move the constant out. So it's k times ax naught. These are my matrix properties that we talked about earlier. Good. And I'm going to put parentheses around this just to emphasize the order in which these operations are happening. I changed the order. Right? I rearranged them. Okay. So now ax1, x1 is still a solution of ax equals b from earlier. So ax1 is b plus k times, now in the parentheses, it's ax naught. Ax naught we found above. Ax naught is equal to 0. So ax naught there is 0. So that's 0. So we have b plus k times 0. That's equal to b. Right? Okay, so you might have, so don't worry about whether or not you would have seen this procedure, right? Don't worry about whether or not you yourself would have come up with this idea. Just understand what I'm doing and just learn the method in which I'm showing, okay? And then you can do it yourself. So eventually at some point. So then what I showed is that a times x1 plus kx naught was equal to b. So that means that x1 plus kx naught for any scalar k is a solution to the equation ax equals b, right? A solution to ax equals b is a vector I can plug, an appropriate size vector I can plug in for x, in which ax equals b. Well, I showed that for any scalar k, x1 plus kx naught is a solution to ax equals b. So from knowing that there is more than one solution, I've actually constructed infinitely many solutions of the linear system, where all I did was I used the scalar k And so it doesn't even matter what the value of that k is, you get the same answer, that a times x1 plus kx naught is b. Okay, so this says that, like I was just saying, x1 plus kx naught is a solution to ax equals b for any of the infinitely many real number values you can choose for k. Thus, ax equals b has infinitely many solutions. Okay, so assuming that ax equals b has more than one solution, we deduced it has infinitely many solutions. And so that means that if more than one solution implies infinitely many, then it can only have 0, 1, or infinitely many, right? It either has more than one solution or it doesn't. If it has more than one solution, it has infinitely many. If it doesn't have more than one solution, it has 1 or 0. And so now there's only 0, 1, or infinitely many solutions. Those are the only possibilities, and it cannot have 2 or any other number other than those 3. And so that proves the theorem. All right, so that's QED, proofs done. Make sense? All right, so that's proof of theorem 1.6.1. That's important to know. Okay, so the next theorem is theorem 1.6.2. That theorem says if capital A is any invertible n by n matrix, then for each n by 1 matrix B, the system of equations ax equals b has exactly one solution, namely x equals a inverse of b. Theorem 1.6.2. If A is any invertible n by n matrix, then for each n by 1 matrix little b, the system of equations ax equals b has exactly one solution, namely x equals a inverse b. All right, so proof. Well, if you start with the equation ax equals b, right? A is invertible. So that means that an inverse of this matrix exists. So multiply both sides of that equation on the left by A inverse. Now, if you multiply on the left side by A inverse on both sides, you can rearrange the multiplication so that's A inverse A times X is equal to A inverse B. That's true by properties of matrices, that it's associative. If you multiply these two in this or these three in this order, it's equal to multiplying those three in that order. Parentheses is denoting order. So here it's saying you multiply these two first and then this on the left. This is saying you multiply these two first and then this on the right. Okay, so in math you can't do anything without, you either have to know something or assume something. So in this case, we know that matrix multiplication is associative. And so we can change the order in which we multiply. Okay, we can't just do that without knowing we can do it, but we can, so it's fine. So now the A inverse A is I, so Ix is equal to A inverse B. Ix, since I is the identity matrix, is just Ix is X, so this is X is equal to A inverse B. So what did I just show? I showed, so let me add some words here. Assume that Ax equals B. And then you draw that conclusion. So what we have found so far is that What we found so far is that X equals A inverse B is a solution to the linear system. Is a solution of AX equals B. Okay, so you can just reverse. You can reverse that and get rid of the assumed. Instead of going in the forward direction here, we go in the backwards one, right? We can multiply on the left by I here. We can multiply both sides on the left by A. So you can multiply both sides on the left by A. It's not quite. You can see how you can get so X equals A inverse B is a solution of the system. I can just maybe I should describe. So let me describe this another way. Okay. So just plug in. So A times now. So you just plug in and A inverse B. So A times A inverse B is B, right? So so what we have found, or just that means, so that means X equals A inverse B is a solution of AX equals B, right? Because I can just substitute X for A inverse B, and you see how that would be equal. So that would be a solution. So we have that that's a solution. So what we also need is that this is the only solution of AX equals B. So we have that it is a solution, but the theorem is saying that it has exactly one solution, namely that one. So we want to know that it's the only. So assume X naught is an arbitrary solution of AX equals B. Well, then what that means is AX naught is equal to B, right? And X naught is arbitrary. Well, assuming that AX naught equals B, we'll then multiply both sides. Okay, so this moves. Okay, so then A inverse, multiply on the left both sides by X naught. And so if you multiply both sides on the left by X naught, by A inverse, you can switch the order of that multiplication by associativity of matrix multiplication. So the left-hand side can be multiplied that way. You have I X naught is equal to A inverse B, but multiplying by the identity doesn't change anything. So this is X naught is equal to A inverse B. Okay, so we assumed that X naught was an arbitrary solution of AX equals B, and we deduced that X naught is equal to A inverse B. So the above tells us that given X naught is an arbitrary solution of AX equals B, that means it must be X naught is equal to A inverse B. So X naught equals A inverse. So X equals A inverse B is the only solution. Is the only solution of AX equals B. Make sense? Okay, and so we've shown that it has exactly one solution, namely X equals A inverse B. And so proof is done. Okay, so that proves that. So once you have an invertible n by n matrix, A, and AX equals B, AX equals B has exactly one solution, namely X equals A inverse B, right? We know it has either 0 solutions, exactly one solution, or infinitely many. And so in this case, when you have a coefficient matrix that's invertible, then we know that AX equals B has exactly one solution, and we know what it is. It's X equals A inverse B. All right. Another example 2 of this section. Solving two linear systems at once. Okay, so we know how to solve a linear system, but now I'm going to show you how to solve two at the same time. So you have x1 plus 2x2 plus 3x3 is equal to 4. 2x1 plus 5x2 plus 3x3 is equal to 5. x1 plus 8x3 is equal to 9. So that's A. And B is the system x1 plus 2x2 plus 3x3 is equal to 1. 2x1 plus 5x2 plus 3x3 is equal to 6. And x1 plus 8x3 is equal to -6. Okay, so you have those two linear systems, and we want to solve them at the same time. So the left-hand side of both systems is exactly the same, right? So we're seeing that they're almost the same. The only difference is that they're equaling different numbers here. Okay, so what we're going to do is we're going to set up a partitioned matrix that describes both linear systems at the same time, because the only difference is the constants at the end that they're equal to. The coefficient matrix is the same for both matrices. So on the whiteboard, I'm going to just write out this partition matrix. So if you write out this partition matrix, this is how you can describe those two at the same time. You have 1, 2, 3 in the top row. You have 2, 5, 3, and you have 1, 0, 8. And now on the two other vertical columns, I'm going to put 4, 5, 9 to 9, 1, 6, -6. So these two vertical columns are representing the constants in the other one. So look at this real quick, and I'm going to go to the whiteboard and show you it again in 3 seconds. 3, 1, 0. Okay, so see, these are the 4, 5, 9, 1, 6, -6. These are the coefficients on the left-hand side, the 3 by 3 matrix part. That's the same coefficients, these coefficients. 1, 2, 3, 2, 5, 3, 1, 0, 8, 4, 5, 9, 1, 6, -6. 4, 5, 9, 1, 6, -6. These are the constants, right? Okay, so when you reduce this matrix to reduce row echelon form, when you get this matrix to reduced row echelon form, R or EF is the abbreviation for reduced row echelon form. So you apply the entire elementary row operations procedure to that matrix to get it to reduced row echelon form. What you get as a result is this matrix. You have the identity matrix on here, and then what you end up here is 1, 0, 1, 2, 1, -1. Okay, so starting out with this matrix, partition matrix on the left, where the columns are the different numbers on the right-hand side of those equations. If you get that matrix to reduced echelon form, the left-hand side here becomes the identity matrix in this example. And the last two columns tell you the solutions to both each of the linear systems. So it follows from the last two columns that the solution of system A is, so then it follows that the solution of system A, so what I'm going to do is I'm going to label this as pink here. Okay. And that was from this one. This is for system A. These are the numbers on the right-hand side for A. This is what it reduces to. And so the solution of A is that x1, see x1 is equal to 1. x2 is equal to 0. And x3 is equal to 1. Right? And so that now you have the solution to you have the unique solution of the first linear system. And it follows that the solution of system A is that, and the solution of system B is, so for B, this column is for system B. It's a reduced echelon form after that was the original column, right? So, and the solution of system B is that x1 is equal to 2. x2 is equal to 1. And x3 is equal to -1. Okay, so all you have to do is write the matrix the way I did originally in the top left, get to reduced echelon form, and the columns will tell you the corresponding values of all the unknowns in those systems. So you get the unique solution in both cases. That's because this original matrix is invertible, and you can get it to reduce echelon form to the identity matrix. Okay, it's possible that your original coefficient matrix is not invertible. You'll get it in all 0 row at the bottom or something, and you could still get all the solutions, but there'd be like infinitely many. So, okay, but this is a simple example in which you get all the solutions. You get the unique solution of both linear systems. Okay, any questions? Okay, good. Okay, so on the whiteboard is the solution to both at the same time. So next is theorem 1.6.3. And so let capital A be a square matrix. That means it has the same number of rows as columns. It means it has the same number of rows as columns, right? As a reminder, part A says if B is a square matrix satisfying BA is equal to I, then B is equal to A inverse. And B, part B says, if B is a square matrix satisfying AB is equal to I, then B is equal to A inverse. Okay, so it just means that B is the inverse of A in both cases. This is for A being a square matrix. and B being the square root. Next theorem is theorem 1.6.4, and it's the equivalent statements theorem, or as I later called it, the equivalence theorem. And same assumption, if A is an n by n matrix, then the following are equivalent. So TFAE is an abbreviation for the following are equivalent. That means all the following statements have the same truth value. Okay? So TFAE is the following are equivalent words, and that means that all the following statements have the same truth value. Okay, so it starts out the same. We're just building on the previous theorem I already said. So here I reminded you of it. And so you already have A, B, C, D here. So maybe I can paste it without the line showing up. Nope. Okay, so I'm just going to do this. I'm just going to recopy and paste. And here, I'm less than 11. Okay, fine, good. Never mind. It's good. Okay, the line's just going to be there. Okay, so E. So I'm going to do is I'm going to have a second line. You can't get rid of a line, make another one. So, so the equivalent statement theorem it starts with these four, right? That these four are equivalent, as you already saw it, and now I'm just going to add more statements to the theorem. So this is also equivalent to all the other ones, making it an even more powerful theorem. So AX equals B is consistent for every n by 1 matrix, little b. And AX equals B has exactly one solution for every n by 1 matrix B. Okay, so statement E says AX equals B is consistent for every n by 1 matrix B. Remember, consistent means has at least one solution. So I'll put them in parentheses for you because it has at least one solution for every n by 1 matrix B. So no matter what appropriately sized, it has to be the right size. It can't be the wrong size. For any appropriately sized matrix B that you put there, this matrix equation has at least one solution. And the solutions are possible vectors to plug in for X, right? X is the unknown. X is the thing that would be a solution. Okay. So for any n by 1 matrix B that's appropriately sized, there's at least one solution matrix X you can plug in there. That's statement E. And statement F says AX equals B has exactly one solution for every n by 1 matrix B. So F is more specific. E says it has at least one solution. F says there's exactly one solution. And so that's statement F. So now we're going to prove this theorem. So we already proved in theorem 1.5.3 that A, B, C, and D are all equivalent, have the same truth value. So all we have to do is now prove that. So the goal is going to be to do this. So if we do this, we show that all the statements, including the new ones, are also equivalent, or all equivalent. So we want to show that A implies F, and that F implies E, and then E implies A. All right. So what we're showing is that both E and F are equivalent. There's actually many ways you can see how this works. One way is you can see that E and F are both equivalent to A. F implies A. If you take any two deductions and put them together, you get another one. So if F implies E and E implies A, that means F implies A. So here, F implies A, but A also implies F by just one arrow. So F is equivalent to A. This also would show if E implies A, that also shows that A implies E, because A implies F and F implies E. So A also implies E. So both of them are equivalent to A. So if A is already equivalent to B, C, and D, and A is also equivalent to E and F, then A is equivalent to B through F. And since everything is equivalent to A, everything's equivalent to each other. Okay, so does that make sense? The point is here, one way, and there's lots of ways you could reason this out. One way to reason it is that by proving this, by showing these three deductions, A implies F and F implies E and E implies A, that both E and F are equivalent to A. And that would mean that A is equivalent to everything, which means that everything is equivalent to each other. Okay, so we just need to prove those three deductions, and we succeed at showing all 6 of those statements are equivalent. So the first proof is that A implies F. We want to show that if A is invertible, then AX equals B has exactly one solution for every n by 1 matrix B. But theorem 1.2, theorem 1.6.2 said if A is any invertible n by n matrix, then for every n by 1 matrix B, the system of equations AX equals B has exactly one solution. If A is any invertible, so you're assuming it's invertible, and then AX equals B is exactly one solution. Well, here, A is the assumption that A is invertible. And so what we're asked to prove is that if A is invertible, then AX equals B is exactly one solution for every n by 1 matrix B. So this was already proven in theorem 1.6.2. Okay, so we already have A implies F. So the next one is that F implies E. So F implies E. Well, what is F implies E? F implies E is the statement if AX equals B has exactly one solution for every n by 1 matrix B, then AX equals B has at least one solution for every n by 1 matrix B. But that's obvious. F implies E is obvious because if AX equals B has exactly one solution for every n by 1 matrix little b, then AX equals B has at least one solution for every n by 1 matrix B. So F implies E is obvious, right? And so we have A implies F and F implies E. So that leaves one more thing to prove. We have to show that E implies A. If we show that, then we're done. And then the extended equivalence theorem is also proven. So E is assuming, so we assume that AX equals B is consistent. It has at least one solution for every n by 1 matrix B. Okay, so that's our assumption. Okay, then in particular, this is true for the following systems. So if it's true for every n by 1 matrix B, then let's look at a short list of n by 1 matrix B and set AX equal to them. And we're assuming that all of these are going to be consistent by our assumption. Okay, so the first one we're going to say is 1, 0, 0, dot, 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 0. AX is equal to that. That has at least one solution by assumption. AX equals 0, 1, 0, dot, 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 0 also has at least one solution. AX equals 0, 0, 1, dot, 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 0. There's only one 0 there. Also has at least one solution. Dot, 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 there's a whole bunch of other ones in between. And then also AX equals 0, 0, 0, dot, 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 continuing zeros within the last one is 1. So then in particular, this is true for the following systems. All the systems above must have at least one solution by our assumption. By our assumption statement E. Okay, let x1, x2, dot, 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 xn be solutions of the respective systems, and let be solutions of the respective system. So x1 is a solution of AX equals this first one. So AX1 is equal to that. The next one is a solution to the second equation. So AX2 is equal to that other B. The third one, AX3 would equal that, dot, dot, dot. The last one, AXN, would equal the last B. Okay, so they're each solution correspondingly with those n equations there, which are all have at least one solution by original assumption. Okay, so we form an n by n matrix using those x's. So we form an n by n matrix having these solutions as columns. Okay, so x1 is the first column, x2 is the second, x3 is the third column, x4 is the fourth column, dot, 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 xn is the nth column. So thus, C, so we form an n by n matrix having these solutions as columns and call it matrix C. So thus C has the following form. C equals so the first column is x1, the second column is x2, and it keeps going dot dot dot, and the last column is xn. But the x's are columns, right? Because we've established that here, having these as columns, having these solutions as columns. So that's where I'm saying you can't tell it from here that they're columns. I'm stating it there. All right. The successive columns of AC will be, so if we take A times C expressed in that way, then we define it that way, the successive columns of AC will be A x1, A x2, A x3, dot dot dot, A x n. Those are the n columns of the matrix AC. Okay, those are the n columns in order of the matrix, in order from left to right of the matrix AC. Thus, the matrix AC is equal to the following matrix. The first column is AX1. The second column is AX2. Dot, dot, dot. The last column is AXN. But we know what AX1, AX2, AX3, and so forth are. The x1 is the solution of AX is equal to this. AX2 is the solution of this matrix equation. AX3 is the solution of this. AXN is the solution of that. So that means that AX1 is this vector. AX2 is that vector. AX3 is this one. AXN is that one. So we can replace these columns by these B's that we chose here appropriately, which are columns of the identity matrix. And so here, so now here, we can just think, in 1 second to build this matrix. If I do it this way, I know that it'll work out nicely. All right, so I think it'll work out nicely. Okay, so then the AX1 is the 1, 0, 0, dot, 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 0 matrix. AX2, right? AX1 is that. AX2 is this. AX3 is that. AXN is that. So AX2 is 0, 1, 0, dot, 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 0. The next one, AX3, is 0, 0, 1, dot, 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 0. And then this continues. So there aren't just necessarily 5 rows here. There could be like 50 rows, though we won't do. You don't have to worry an exam, probably, with that happen. But I'm just continuing, so I'm not saying how many rows there are here. And the last column will have a 1 at the bottom and 0 everywhere else, right? So now we see the AC has to equal this matrix. That's the identity matrix. It has the same number of rows as columns. Okay, so that's the identity matrix. So what did we just show? We showed that A was invertible, right? So thus, A is invertible. Okay, we could show that we can multiply a matrix on the left by A and also get the identity. So thus, A is invertible. Okay, here. Wait. By theorem 1. So theorem 1.6.3 says let A be a square matrix. If B is a square matrix satisfying AB is equal to I, then B equals A inverse. So by part B of this theorem, we don't have to show both sides. We could just say that because we found another square matrix in which we multiply on the right by A times B, we get I, then that matrix is the inverse, right? That means that A is invertible, right? Not only do we conclude, well, if we conclude that B equals A inverse, it also means that the A originally is invertible. So thus A is invertible by theorem 1.6.3, part B. Okay, and so that's what we want to show. E implies A. A is a statement and A is invertible, and so we are done. So that's what we want to show, and we showed it right there. So we succeeded showing that E implies A. So we proved A implies F. We showed F implies E, and we showed that E implies A. So we proved all three of these deductions, and so we proved that all 6 of these statements are equivalent. And so, so our conclusion is that all 6 statements are equivalent. Okay, the proof is done. Right, and so now we finished the proof of the extended equivalence theorem. We'll just keep calling it the equivalence theorem, and we're going to keep adding more statements to it. And so we'll just keep extending it. There's going to be a lot more, but at this point we have 6, and there will be a lot more. Okay, we'll stop there. There's more there's homework. We finished 1.5. So since we finished 1.5, I can assign homework for 1.5. So 1. Okay, so do you see that? No, now you do. Okay, so for 1.5, I'm going to assign this for homework for 1.5. 1, 5, and 10. Okay, exercise set 1.5, 1, 5, and 10. So for the homework, it's exercise set 1.5, numbers 1, 5, 10. Exercise set 1.5, 1, 5, 10. 1.5, 1, 5. Good. Okay, so that will be due next class. Okay, so this is homework due next class. Okay, next Tuesday. So that's 10/12/2021. Okay, so exercise set 1.5, numbers 1, 5, and 10. All right, and so that's it for today. Have a nice weekend. Thank you everyone for being here. We're going to stop the recording.